Dear students, today's video lecture deals with Lrk Grammars. We had a grammar having so many production rules, and we start from the start symbol S and apply production rules on it, and we reach at some strings after application of production rules, and these strings were known as sentential forms. And if the string contains terminals only, then it is called sentence. So sentential forms and sentences. Okay, this time we will deal with parsing of a string. This means that we have a string containing variables and terminals, and we will form a reverse derivation which will be specifying what sequence of production was used to achieve that string. So parsing basically can be done in two basic methods. First one is bottom up and the second one is top down. In the bottom up method, rightmost derivation is used and it leads to Lrk grammars, and the top down approach of parsing a string, which we had learnt in earlier chapters, this uses leftmost derivations and it leads to Lrk grammar. We will differentiate it, and we will differentiate between Lrk and Lrk grammar. But before that, let's understand what are they basically. So now reverse derivation of a string is the major concern in this chapter. We start from here. To find a derivation tree for a given sentence W. You can well imagine W is a string, and according to our earlier notations, we can start with W and replace a substring, say W1 of W by a variable A. Means in this string a part or substring can be replaced with A if there is a production of the type A to W1. So means we have a string W and a part of it. If it matches with W1, it will be replaced with A, and we will get that string which is one step earlier in the derivation. So this way parsing can be done, and we repeat for the same procedure on the earlier on this string, and then we move back to the starting symbol S. So once again I repeat, you take the string W. If part of it matches with the right hand side of a production, then it is replaced with left hand side, because we are reverse traversing the string, so it will be replaced with capital A. And similarly that string also, if part of it matches with some other right hand side of some other production, it will be replaced by this, and so on. We will go on and we will reach the start symbol. But it cannot be done so easily. For example, if there are situations that more than one productions can be reversed here, so it is very difficult to decide which production was used in the previous step. So it leads to an ambiguity. Maybe first production have been used, maybe the other production have been used. So this is not so easy to be done. Let's take this concept. Consider some sentential form alpha, beta and W, where alpha and beta, as per our notations, alpha and beta belong to Vn, means set of variables, and union with sigma set of terminals. So string star, this means that alpha and beta are the strings over variables and terminals, but w belongs to sigma star, means w contains no variable, it contains terminals only. So this string is broken up into three parts, alpha, beta. These two substrings are having variables as well as terminals, but the third string w is purely terminal string. Suppose we are interested in finding the production applied in the last step of the derivation for this string. If a to beta is a production, then this beta can be replaced with a. It is likely that a to beta is the production applied in the last step, but we cannot definitely say that this is the case. If it is possible to assert that a to beta is the production applied in the last step by looking ahead for k symbols, means in getting this string, suppose this production was used, so it would have become alpha a w, which derives alpha beta w. If it is sure that this production was used, then it's okay, but it is never so. So some other production may have been yielded this string. So if we can assure that this production, this specific production was used in derivation of this string in the last step, this can be done by looking on the symbols ahead of the beta, means we are using the right hand side of this string, this production, it ends here, and we can look on to the string further, for example in this case w. So we can look forward for one symbol or two symbols or three symbols to assure that this production was used or not. This can be made more clear when we will use an example. So if we can assure that this production was used by looking at k symbols ahead of beta, then the grammar used will be known as Lrk grammar. So the production this production which is in question, which is to be checked whether this was used or not, is known as Handel production, and the right hand side of this production is called Handel. So I will use this word frequently, so keep in mind that Handel is the right hand side of the production which is to be checked. So Handel, production, and Handel. So after Handel we look at a few symbols, 1, 2 or 3. So depending on that number, let us suppose we look at k symbols, depending on that symbol we can classify our grammar as Lrk. So Lrk means first L in this notation indicates that this is from left to right scanning. So if we scan this string in left to right sequence, we see, look at the first symbol and the second symbol and the third symbol and so on. So first L indicates the scanning of the input symbol is from left to right. The second character R in this notation means rightmost derivation is being done. Hope you understand it very well. Rightmost derivation means when you are deriving a sentence, a string, the rightmost variable is replaced with some other string every time. So following this sequence it becomes rightmost derivation. So left to right scanning, rightmost derivation, and k symbols are being watched to ascertain which production was used in the last derivation. So such kind of grammar will be classified as Lrk. You will face LR0 grammars in which no symbol will be required to checked, and similarly you will have LR1 grammar in which one symbol ahead of the handle will be seen to ascertain the application of production. Similarly, you can have LR2 grammars in which two symbols will be checked before ascertaining the application of the production. So rightmost derivation is clear. Let's take on make the concept more clear by looking at this example. So this example has a grammar with these a few productions. It is easy to see that LG generated by this grammar is this. So let's look at this, how this is achieved. So this is the grammar. These are the productions used in the grammar given in the example, and there are a few trees, derivation trees, which yield different products. So let's look at the first derivation tree. S is the start symbol. We apply the first production S to AB because it is the only S production which can be applied. S to AB is the first application of the production. So I am taking the step-by-step movement derivation in this sequence also. S to AB, we achieved it at the application of the first production S to AB. Then because this is a leftmost derivation, we will apply our productions at the leftmost symbol. So this is the leftmost variable, so it will be applied some production. There are two A productions available, A to AAB and A to null, which can be applicable. Suppose I apply AAB first production, A to AAB. So the string becomes A, small a, capital B, capital B. This. Right? Now the leftmost variable in this string is capital A, which can be applied in two manners also. So let us suppose we apply it. We apply this string A to null to this. So this way we get A, null is excluded, A, B, capital B. So A, capital B will be the next string yielded. So similarly, this time B, capital B is the leftmost symbol. So if you apply production, you have two choices, B to BB and B to B. So let us suppose I apply B to small b here. So next string yielded is A, small b and capital B. So B is replaced with B. Similarly, the next leftmost variable is this B. It can be replaced in two different ways. Let us suppose we are taking this production again and we reach ABB. So this string is all terminal string, so no further replacement can occur. So all terminal string means this is a sentence, and these are the sentential forms, right? So this way we got A1, B2. This can be written in this form also. Another derivation tree is given here, and application of production, sequence of application of production is given, and the yield you achieved is A, small b, small b, can be written A to B3 also. So this is all terminal string, so it can be classified as a sentence, and these are the sentential forms. If you generalize it, the sentences formed by this grammar are A1, B2, A2, B3. If you see more derivation trees, you will observe that it will lead to a grammar, lead to a language which contains A followed by B's. But number of A's should be less than number of B's, and at least one A and one B should be there. So this can be written as AMBN, where M is smaller than N and both of these are greater than 1, means at least one A should be there and B should also exist in the symbol. So this is the language generated by it, and these are the sentential forms. If you take because they contain variables, so these are the sentential forms. So sentential forms can be generalized by this. If you observe it carefully, you will see that all the sentential forms contain capital A, then they contain capital B, then they contain small b's. Right? This can be generalized as this: A, capital B, and small b raised to the power k, means repetition, iteration of small b symbols. K can be 0. If k is 0, it will become AB. If k is 1, it will become ABB. If k is 2, this, and so on. So these are a few sentential forms. More sentential forms are also possible. So let's move on to the let's take the similar example. Now we are concerned with parsing. For example, parsing means we want to find the reverse derivation tree. We don't know how the string is achieved. We just know AABBB is achieved. So what was the last production used here? So if you look at it, can you judge without looking at this table, this graph or tree? Can you judge which production was used earlier? Okay, this B, if we take rightmost derivation, this B could have been replaced with capital B. So one step earlier, it would have been A, capital B, means this. It's okay. But before that, this production may also have been used: A, capital B, small b. But here in this case, this does not form the sentential form. If you observe the sentential forms, it says that you have a, small b, then it was capital B and small b. So capital B after small a, small b. This does not have this is not contained in the sentential form. So we can judge. Similarly, take another example. Suppose we are at this position, AB. By looking at it, we can judge that AB would have been achieved by using these production S to AB. Right? Similarly, here in this string, look at the partial string AB. It may also lead to the decision that this production have been used here also. But if this production was used, then its one step back would have been A, capital S, B. So A, capital S, B is never a sentential form. You can look at it. A, capital S, B is not a sentential form. So we conclude that this is not a production used at this step. So S to AB can be inferred that S to AB production was not used to achieve this string. How did you decide it? You looked at this is AB, this is the string, handle string, and this is the handle, and handle after handle after the handle you look at the next symbol B, it becomes SB. So you decide that this is not the production used in earlier case. In this case AB was the handle, and you look at the next symbol, there's nothing, so it leads to S, which is a start symbol, means it is a sentential form. So this way, by looking at the just one symbol to the right of the handle, you can decide whether this production was used or not. So this is an example of Lr grammar, because we look one symbol ahead of the handle and we decide that this production was used, and we similarly here in this case we look one symbol to the right of handle, we decide that this production was not used. So this decision is based on looking at one symbol ahead of the handle. So this is Lr grammar. So now let's go to the formal definition of Lr grammars. Let G is equal to Vn. Vn is set of non-terminal symbols, means set of variables. Sigma is set of terminal symbols, and P is the set of productions, and S is the start symbol. So G is a grammar, and this grammar is context-free grammar. Context-free grammar, if you remember, contains production rules of type A to alpha, in which right hand side contains just one variable and left hand side should contain just one variable, and right hand side of the production may contain a string. So context-free grammar. Now another condition, S derives at S itself by using n steps. N is when you put a star on the derivation, means it's a multiple step derivation. When you put 1 means it's a one step derivation. When you write 2 here, it means it's a 2-step derivation. When you write n here, that it means that it is a n-step derivation. So after n replacements, S reaches from S to S itself only. So if this is so, only when n is 0, means no step is taken. So therefore any kind of production which leads from S to S itself does not exist. G is an Lrk grammar where k is greater than or equal to 0 if, number 1, S start symbol derives alpha A W. So start symbol derives a string which is broken into 3 parts. The rightmost part is the string of terminals only, so no variables in this part of the string, and A is a symbol variable, so single variable, and alpha is a string containing variables as well as terminals. So this part of the string can contain variables. This is of course a variable, and this part of the string does not contain any variable. So start symbol derives it. This star means that after multiple replacements we have reached here, and R on the bottom of this symbol means the rightmost derivation. So rightmost derivation from S yields you alpha A W, and afterwards, after moving one more step, rightmost derivation of this string will be, because all of these are the terminals, this is the rightmost symbol, so this will be replaced with another string, so it gives you alpha beta W. So from S we have reached at alpha beta W, and in the last A to beta is the production which is used. So this is the first step, derivation. You have another derivation from the start symbol. So you use multiple replacements in the rightmost derivation manner, but reach at some different string. So this string is different from it. So it is indicated by alpha dash, a dash and w dash. And after that one more replacement was done, because this is all terminal string and the rightmost symbol, variable symbol, is a. So a will be replaced with beta dash, right? So ultimately you reach at this symbol. Okay, so now starting from S, you have reached at this string as well as this string. So these are the two sentential forms which are yielded. The first, alpha plus beta, this means length of alpha beta. So alpha and beta concatenated and afterward length. So means this in this string length of alpha beta plus k symbols, alpha after alpha beta, k more symbols of alpha beta and w, and similarly k more symbols alpha dash beta dash w dash coincides, means these are the same. So this means that in this string and in this strings, first a few symbols are matching in both the strings. For example, alpha, beta and a few symbols of w of this string, and alpha dash, beta dash and the same number of symbols in the w dash string match each other, right? Then then alpha should be definitely equal to alpha dash, a should definitely be equal to a dash, and beta should also be definitely equal to beta dash. So a definition of Lrk grammar is that if we start from S and we reach at two different strings in which a particular number of symbols after beta and the same number of symbols after beta dash match each other, then alpha and alpha dash, beta and beta dash, and a dash should match. So this gives you the definition of Lrk grammar. This eventually means that after the handle, because in the last we are using the production a to beta. So a to beta is the handle string and beta is the handle. So after handle, a few number of characters match with the same number of characters in this string. So then there is no ambiguity there. This means that alpha to beta used here and alpha dash to beta dash used here are the same, because a is a dash, b is b dash. So now this specifies that the particular production a to beta is used in reaching this string. So this gives you a definition of Lrk grammar. Let's take another example. G be a grammar, S to AA and A to BB, and the third production. And we have to show that this is a LR0 grammar. LR0 grammar means that we do not need to look at any symbol. We need to look at 0 symbols ahead of the handle to ascertain, to make sure that this production was used. Let us move on to the example. This is the same grammar I have taken, and derivation can occur in this way. There is one production S start symbol, so this will be the way we go, S to AA, and after that A can be replaced in two different manners, A to ABB and A to B. So if we use A to B, it becomes AB. So S to AB, so this is a sentence because it does not contain any variable, and this is a sentential form. And if we use the second method, A to replace A, we can get A B B, right? This contains variable, so it is not a sentence, it is just a sentential form. And in this form, again, if we are obviously we are having just one variable, so it is the rightmost derivation automatically. So A can be replaced using this production, will give you this yield, which is a sentence. And the same A can be replaced by using this production, which will give you A B B B B. And similarly you can go ahead. So these this is the derivation. So if you work on the language generated by this grammar, means you generalize these sentences. You have A B, you have A B B B, you have A B B B B B. So A followed by B is the first conclusion. Secondly, the number of B is either 1 or 3 or 5 or 7 or 9, etc. Means odd number of B's, right? So you get A, B, 2n plus 1. So this is the way to represent an odd number, A, B, 2n plus 1, where n cannot be 0, because if it is 0, it is just an A, which is not the sentence. So this is the language generated by this grammar. And let's generalize sentential forms also. If you observe them carefully, all of them contain a small a in the beginning, and afterwards it contains capital A. So every string in this sentential forms is preceded by small a, capital A. So this is a prefix, and afterwards we are having 0 number of B, 2 number of B's, 4 number of B's, 6 number of B's, even number of B's. So B 2n is a way to represent even number. So B 2n, right? So these are the sentential forms, A B 2n. Here n can be 0 also, because if it is 0, it becomes A, which is also a sentential form. If it is 1, it becomes A B B. If it is 2, it becomes A B B B B, and so on, right? So now, if you start from anywhere you pick, let us suppose this is the symbol. You want to see which was the earlier production used in the derivation. Which production was used to yield this string from the previous string. As there is just one symbol, right? So one symbol would have been used. Just a minute. Suppose at this level, you judge that this production was used at this place, right? So the string preceding it would have been A, small a, capital A, small b, small b, small b, capital A. It violates this sentential form. If you see it, observe carefully, only A existing in this sentential form is preceding B's. So after B there is no A. So after B, if you have used this production, after B there would have been A. So which violates the sentential forms. So this means that it was not used here. Similarly, if you go here, A, right? So you will have A, small capital A, then small b, then capital A. Means after B, another capital A after B will a violation of the of this sentential forms. So this means that this production was not used, right? So you can clearly judge that ABB in this sentence, ABB was the handle of this production handle. So ABB, on using this production, you will have A, capital A, B, B, which is a valid sentential form. So this means that at this level this production was used. So you are ascertaining it that this production was used without looking into BBB. You have looked at the previous symbols, not in the symbols ahead. So without looking at any symbol to the right of the handle, we have decided that this production was used and this production was not used. So therefore it is an example of Lrk grammar. This way you can have more examples. You look into you go through this example with a greater detail. It's an example discussed in the previous example, and you have to prove that this is Lr1, not Lr0. It can be shown very easily in the if you remember in the last example, first example we used to first example, which is this. In this example we could ascertain which production was used on looking at the next symbol, one symbol to the right of handle. So therefore it would have been an Lr1 grammar. Now let's move on to properties of Lrk grammars. First property, every Lrk grammar is an unambiguous one. Which are the ambiguous grammars? Which have if the grammar has two different derivation trees to yield the same string, then the grammar was known as ambiguous one. So this means that every Lrk grammar, Lrk is a subclass of context-free languages, CFL. So CFL may have some ambiguity, but Lrk is unambiguous, means there is no string governed by this Lrk grammar which has more than one, I repeat, more than one derivation graph, derivation tree. So every Lrk grammar G is unambiguous grammar. Let's move on to the second property. If G is an Lrk grammar, there exists deterministic push down automaton A accepting LG. So LG is the language generated by this grammar, which is Lrk. So this grammar and you can form a deterministic PDA. Hope you understand it very well, what that we had studied in previous chapters. You can design a deterministic push down automata which accepts this language. This generally means that to every Lrk grammar you can form an equivalent deterministic push down automata, push down automaton. Next property is, if A is deterministic push down automaton, then there exists an Lr1 grammar such that language generated by G is equal to the set of strings accepted by automaton, push down, PDA. Right? This is the vice versa of this property. It says that every Lrk has an equivalent push down automata, and this says that every push down automata also has an Lr1 grammar. Lr1 grammar means look ahead, number of look ahead symbols is 1. So next property, number 4, if G is an Lrk grammar where k is greater than 1, k can be 1, 2, 3, 4, etc., then there exists an equivalent grammar G1 which is Lr1. See, this is very important. So it says that if you have an Lr5 grammar or if you have an Lr2 grammar, you can form equivalent Lr1 grammar also. So all the grammars, Lr grammars, can be reduced to Lr1 grammar. So it's important to study Lr0 and Lr1 grammars only, because beyond that, if you have Lr2 grammar, you can have an equivalent Lr1 grammar. There are methods to convert it. Now comes definition. A context-free language is said to be deterministic if it is accepted by deterministic push-down automata. Right? An automaton can be deterministic, so language accepted by that will also be deterministic, and non-deterministic push-down automata will have non-deterministic push-down language, non-deterministic language associated with it. Property number 5. The class of deterministic languages is a proper subclass. Proper subclass means that it contains some elements which are not of context-free languages. Just a minute. The class of deterministic languages is a proper subclass of context-free languages. This means that it is a proper subclass, means there are a few languages which are non-deterministic also. Right? The class of deterministic languages can be denoted by LDCFL. This D indicates deterministic. So context-free language can have non-deterministic element also, but excluding that and having only deterministic elements, we get DCFL. Now next property, LDCFL, deterministic CFL, is closed under complementation. Closed under complementation means closure property means that if A complementation, if A is closed, if an element A is a part of this language, A belongs to this language, X, you take X, if X belongs to this language, then its complement also belongs to this language. This means that closed under complementation, but not under union and intersection. Means X and Y are two languages belonging to this. If their union is taken, that may not belong to this. If their intersection is taken, that may also not belong to it. Okay, now let's move on ahead. Definition 8.3. A context-free language has prefix property if no proper prefix string of L belongs to L. Means if you take a string from this language and its front portion does not belong to the language itself, means if you take any string from the language, you take first a few characters of it, means prefix, but this you cannot choose any prefix that is also part of the language. Means it's not a concatenation of two languages like this. So such kind of property, if it is followed, it is known as prefix property. So next property deals with it. A context-free language is generated by an Lr0 grammar if and only if it is accepted by the deterministic pushdown automata and has a prefix property. Means if we have to prove that a language is a CFL is Lr0, then we will show that it is represented by a deterministic PDA and secondly it follows the prefix property. These two conditions will be sufficient to prove that the language is LR0. In the last property, there is an algorithm to decide whether a given context-free grammar grammar is LRK. So to prove any grammar to be LRK, there exists a proper algorithm which you can follow and prove that. So now next topic is closure properties of languages. So first of all, think that L0 is type 0 language, LCSL is context sensitive language, then we have context free language, and then we have regular language. So each of the classes L0, LCSL, LCFL, RL, it's RL not TL, is closed under union. Means if A, B, C are the sentences from the L0 language, and D, E, F are also the sentences from the L0 language, then its union A, B, C, D, E, F also belongs to this language. So it is closed under union, and it is closed under concatenation also, and transpose operation also. Transpose means transpose of a language, means its productions are left hand side and right hand side of the productions are reversed. For example, if you have a production like this, AB to CDE, AB to CDE, then if you reverse the order on both sides, it becomes BA on the left hand side and EDC on the right hand side. So you take this production BA to EDC. So productions of this kind means reversed strings on the left hand side and right hand side both of all the productions give you transpose of the grammar. So if a grammar generates CSL, then its transpose will also generate a CSL. Property number 2, regular language is closed under intersection and complementation also. So only regular language follows this property. Intersection and complementation both are closed. Third property, CFL is not closed under intersection and complementation. So context free languages are closed neither under intersection nor under complementation. So with that we have completed all the topics in this chapter. Next are a few examples, you can take them up, and then you have multiple choice question also. Let's try them. An Lrk grammar has to be a type 0 grammar, type 1 grammar, type 2 grammar, or none of these. It's a type 2 grammar because we have clearly said that Lrk is a subclass of context free languages which are type 2 grammar. Next one is Lrk grammar is always unambiguous. Always ambiguous. We have read it very clearly that Lrk grammars are always unambiguous. Handle means right hand side of the handle production is a string of variables and terminals, string of variables, string of terminals. So it's a string of variables as well as terminals. Similarly, next question, the automaton corresponding to an Lrk grammar is deterministic finite automaton, non-deterministic